Hi everyone. So in this video we will be sort of reviewing the topic of macroscopic balances that has been discussed in lectures in last 2 weeks. But we will also specifically focus on the concept of F star. So we have been getting a lot of questions on the concept of F star, which seems to be a little more confusing than the other topics. So we'll review the whole content of chapter 11 and 12, basically mainly chapter 11 and then also chapter 12. Go into macroscopic balances, sort of review the material and specifically focus on F star, and then I will do an example problem to sort of help you understand what does F star mean and what will be the value of F star in few cases, which will hopefully clarify some questions. So let us start with writing macroscopic balances. So we have discussed three kinds of balances: mass balance, momentum balance, and mechanical energy balance. So we derived the equations in class in both vector form and then we did it for discrete openings. I will just be discussing the discrete openings because discussing the vector form will take a lot of time. So we'll just focus on discrete openings for the purpose of this video. So in mass balance, we discussed that the equation for two discrete openings, that's just for a simplified case, for two discrete openings is given by dm by dt is equal to w1 minus w2, where w1 is the inlet and w2 is the outlet. So we can choose we can see which in our control volume which is the opening which is having some mass coming in and some mass going out. So this is just an equation of conservation of mass. So the units of dm by dt are kg per second. This is w1 is also kg per second and this is also kg per second. Right. So all this says is that mass accumulated. So this says that mass accumulated is equal to mass in minus mass out, and that's about it. So that's all this equation is saying. And as you can recall, we have also described W1 as rho 1 V1 average S1. So this is the cross-sectional area S1 through which this velocity is flowing minus rho V2 S2. Okay. So the units of V1 are meter per second. The velocity in the first opening, and S1 is the area of the first cross-sectional area. And this is rho square, and the units of rho 1 are kg per meter cube. So if you multiply, you will get kg per second. So this is the mass flow rate basically. So mass flow rate in minus mass flow rate out. So we can just imagine something simple because we have two openings. Let us imagine we have a pipe like this. The area here bs2 and here s1. The velocity here is v1 average and v2 average. And if we assume steady state, we will get 0 is equal to rho 1 v1 s1 minus rho 2 v2 s2. So assuming that the flow is happening in this direction, so the mass in is in this control volume and the entire control volume of the pipe is 5. Mass in is rho v1 s1 and mass out is rho v2 s2, and rho 1 is equal to rho 2 because there is no change in density. We can assume that for most of the liquid cases, or in other words, v1 s1 is equal to v2 s2. So this is a very common formula which you will use for two openings, that velocity times area of the first opening is equal to velocity times area of the second opening. If you have just two openings, then one is inlet and one is outlet. And you can imagine that if you have smaller opening, in terms of area, you will have larger velocity. So this is also intuitive that for instance, in a pipe, if you squeeze the pipe and you decrease the area of opening, the velocity increases to maintain the constant flow rate. So basically, this is very straightforward, that if you have dm by dt is w1 minus w2, inlet minus outlet. So mass accumulated is equal to mass in minus mass out, and the expression for mass over an opening is given by rho times velocity times average velocity times area, right? And you just have to balance the two, inlet is equal to outlet if it is steady flow. and most of the cases we will deal with steady flow. So now, one thing that I have implicitly assumed here is that the flow is perpendicular to the cross section, and that is generally the assumption we have done while deriving this equation of dm by dt is equal to w1 minus w2. So this is just sort of a refresher. I hope that you are sort of able to follow that what I did here. Just writing the expression of w1 is rho1 v1 s1, w2 rho2 v2 s2, and equating them, and obviously assuming that rho1 is equal to rho2 because it's a liquid and we can assume constant rho. Okay. So this was the part of the mass balance. Okay. So now let's switch gears and talk about momentum balance. Again, we did a lot of uh, derivation here, but I'll just directly give you the last equation that we had derived for two openings, and again this is only for two openings, and then we can discuss in more detail about this. Okay, so this is what the equation that I'll be writing is equation 11.37. Again, I am assuming two openings, and there are several assumptions like planar cross sections, velocity normal to the openings, and so on. So you can read the assumptions in the book, but after assuming all of these things, we get the equation f star is equal to minus of p1 plus rho 1 of v1 square into n1 s1 minus p2 of rho 2 v2 square of n2 s2 plus mg, and this is also a vector. Okay, so first thing, this is a vector equation. Do not forget this. This is the important thing. This is a vector equation because you want to calculate the force, and force is a vector quantity. Now, what is F star? I think this is the point where most students get confused. So, F star is the force applied by the fluid on solid walls. So in macroscopic balances, in any macroscopic balances, you need a control volume. For instance, we had a control volume of the whole pipe here, so expanding pipe, right? In this control volume, there are some open surfaces and there are some walls. So for instance, this part, the side here, both are walls, and this here is opening. Opening can either be inlet or can be outlet. Okay. So the way macroscopic balances are derived is that what we want to do is by understanding the pressure and velocity variations at the openings. So S1 and S2 are openings. By understanding the pressure and velocity variations at the openings, we can calculate the force applied by the fluids on the solid walls. So why is that important, or why is that even interesting for us, is because, as you can recall, to calculate F star, so for instance, if we had a flow going through this pipe, to calculate the uh, on, force on this particular part, we'll solve the Navier-Stokes equation, we'll get the velocity profile, then we'll find the shear stress at this point, and then integrate the shear stress as it is going along the length of the pipe to find the entire force. Now, just by using inlet and outlet, we can actually get the force on the walls. So this is a macroscopic balance, and we don't have to start from a microscopic velocity profile and then find the area, find the stress, and then find the force and integrate over the entire area. So basically, what momentum balance in a macroscopic sense allows us to do is to utilize the information from openings, again inlet and outlet. Openings can be both inlet and outlet, and use it to calculate the force applied by the fluid on the solid walls. So I hope this is clear. So if we are in a system wherever we have some solid walls, and we can construct a control volume such that we understand the pressure distribution on the opening, inlet and outlet, based on that information we can calculate the force applied by the fluid on solid walls. Okay, so for instance, let us take an example just to sort of drive this point home, is that if we have a pipe like this, right, let's say we have a pipe like this, and we want to find the force and the fluid is flowing in this direction. If we want to find the force on walls applied by the fluid, if you have been asked to calculate the force on walls applied by the fluid, then we don't have to always know the details of the velocity. If you know the velocity u here, the velocity will come out here. Let's say this is the average velocity v1 is actually equal to u. You can imagine that if the areas are same here and I use the v1 s1 is equal to v2 s2, because s1 is equal to s2, v2 will also be equal to u here. And if I take the control volume to be the entire pipe, right, so the F star will be equal to minus P1 plus rho, and rho will be constant, so constant rho into V1 square, which is actually Vu square. Now this is important, the normal is always taken, the normal here is taken going away from control volume, going away from control volume. So in this case, let me call this minus EZ. I'm just doing it very quickly to show you something. Into S, surface area of this circular part is, let's say, S, and then we'll have minus of P1. So this part that I have written is same as this part, okay, which is minus pressure plus rho u square into normal into S minus P2 plus rho u square, because pressure, I have taken the pressure here, outlet, and then rho u square, rho is constant and V2 is equal to u, because it's the equation of continuity or the mass balance, into the normal in the second surface, the normal here, the second surface here would point away from the control volume, so it will point in plus z. So let's call this z, let's call this r, just to be clear, z into s. Okay, so let me write this here. So if you calculate f star, f star, this basically becomes P1 minus P2 into S into EZ. So what are we saying? What does this force mean? What all we are saying here is that as long as we know the pressure here and the pressure at the outlet, pressure at the inlet and pressure at the outlet, we can just subtract the pressure and multiply with the circular area here to calculate the force on the walls. And that is kind of intuitive, right? Because the force, because the fluid is basically applying the force and trying to push the wall towards plus z direction, and the wall is resisting that by applying the shear stress. That is something we have discussed. So as long as there is some pressure drop, we can estimate the force, and we just need the pressure drop, and measuring pressure drop is easy. You just need a pressure gauge and you can basically find pressure drop in any pipe. So this is just to sort of give you an example that this F star is in any problem of macroscopic balance, F star is always the force applied with the fluid and the solid walls. So it is the on the entire circular region here, on the entire circular side of the entire all the walls basically here, the circular walls, combined force is this F star. Okay, so I hope it makes sense. So I have discussed the mass balance. I have discussed where I have discussed that W1 is rho 1 V1 S1. V1 is the average velocity. Then I have discussed the, the the momentum balance, where basically I have discussed trying to explain the F star. Just a quick note, just in case anybody gets confused, I assumed implicitly here that the flow is turbulent. I'm sorry if there was any confusion, because I assumed that V1 is equal to U and V1 square is equal to U square. Recall that V1 square is not necessarily equal to V1 whole square for laminar flow. I have assumed in this problem while solving that the flow is turbulent. Okay, it will not change anything in the answer, final answer. It will still get cancelled everywhere, but just so that you understand that I've assumed implicitly that the flow is turbulent in both inlet and outlet. That is just an assumption. This was just to demonstrate basically what we are calculating here is the flow, is the force experienced by the circular portion of the walls, which are circular in nature, due to the flow of the fluid through the pipe. Okay, so for instance, you can also recall what we did in the recitation when we had fluid like this, right, in the pipe, and then we had a bent nozzle also, fluid going inside. So the F star was again the flow of the force caused on these walls, the circular walls here, because of the fluid flow. So that is what F star is, and I will go into more details through the example that we will discuss. Okay, so I hope this makes sense now. So we have discussed mass balance, we have discussed momentum balance. Just again a side note that V1 square mean is not always equal to mean of V1 square, and it will only be true for turbulent flows. Okay. Now let's go into the mechanical energy balance. Again, the derivation is quite long, and I will just be discussing uh, the final form that you get from mechanical energy balance, which is the engineering Bernoulli's equation. So I'm just directly writing the engineering Bernoulli's equation, and this is equation 11.46. Okay, that is what I'll be writing. The engineering Bernoulli's equation states that delta, which is delta is, we will take 2 points to describe this. Delta of V cubed by 2 of V plus T by rho plus GH equal to 1 by W into Wm minus EC minus EB. Okay. So what is this equation of mechanical energy balance saying? So this part is the kinetic energy, this part is the pressure energy, hydrostatic energy, this is the gravitational, and again like momentum balance, mean of V cube is not equal to mean of V whole cube unless the flow is turbulent. If turbulent, you can assume mean of V cube to be V of cube. So, and if laminar, this is the case, if turbulent, this is the case. Okay. So this purpose of this video will assume the flow to be turbulent and just assume this. Okay. Now, What is W? W here is the mass flow rate, which we have defined before also, and this is given as rho times V times S, wherever the velocity is in the cross-sectional, the corresponding cross-sectional area. This is the work, uh, basically that the energy put into the system because of any piping and any turbines and things like that. So energy put in, energy input due to any pumping, piping, something like that. EC is commonly known as the because of the mechanical loss of mechanical energy due to compressibility. So this is loss of energy due to compressibility. Compressibility. So I'm not elaborating on EC because we won't be using. And EV are the viscous losses. Viscous losses. Okay. So now let us discuss a little bit more about each of these points. So what we are saying, what this mechanical energy balance is saying, that the change in kinetic energy plus pressure energy plus gravitational energy is an engineering Bernoulli's equation. So if at point 2 I'm trying to calculate this total mechanical energy, it would either be greater or less than the energy calculated from point 1, and what will increase the energy is the pumping, or if I'm trying to put any energy in the system. What will decrease energy at point 2 is if I have some mechanical loss due to compression or loss due to viscous forces. Okay, so this is something we have discussed in class. I'm not going to be elaborating on this, but I hope you can sort of understand based on lectures that this is just basically saying that if at point 2 in my system I have less energy than point 1, by energy I mean sum of mechanical energy, it is basically the net right hand side here will be negative, because if 2 is less than 1, then delta will become negative. So we'll write delta basically means we'll write this as v2 cube by v1 p2 by rho 1 p2 by rho plus gh2 minus v1 cube by 2v minus v1 by rho minus gh. So basically 2 minus 1, and if that is negative, that means that this right hand side was negative. That means maybe viscous losses were overpowering energy input, compression losses were overpowering energy input, or maybe there was zero energy input and there was just viscous losses and things like that. But you are well aware about basically how we derive this equation in the class. So let us recall what all we have discussed in this video. So we started with discussing of mass balance, that dm by dt is equal to w1 minus w2 for two openings, inlet and outlet. And for steady state, mass in is equal to mass out, or rho 1 v1 s1 is equal to rho 2 v2 s2. For constant rho, v1 s1 becomes equal to v2 s2, or that velocity times the cross sectional area is same in the entire system. Then went into momentum balance, where we discussed F star, which is the force applied by the fluid on solid walls, and it is dependent on the pressure and velocity profiles only on the openings. So without knowing any details about the flow inside the system, we can calculate F star. Alright, it is a vector equation and it involves V1 square mean is not equal to mean of V1 square. If it is turbulent, then only that is equal. Okay. Then we went into momentum energy balance, mechanical energy balance, where we discussed that the total mechanical energy, which is the kinetic energy plus pressure energy plus gravitational energy in the system, the change in that total energy is dependent on the energy input due to pumping, and loss due to compression, and loss due to viscous energy. Okay, so the whole point of this entire exercise was to sort of make you a bit familiar with all the things we have discussed. So let us just recall very quickly what we have written so that I can use it very easily. Mass balance, we basically said W1 is equal to W2, so I'm assuming steady flow. Then for momentum balance, we said that F star is equal to minus of V1 plus rho of V1 square S to S1 N1 vector minus P2 plus rho V2 square into S2 and 2 vector plus 1 G. Finally, the energy balance or the Moody's engineering equation is delta of V Q by V Q by 2 of V plus P by rho GH 1 by W, let's call this W, 1 by W into capital Wn minus EC minus E. Okay. So now let us do a problem to sort of understand a little bit more about F star, but we will need all other things to actually solve the problem. So the problem is that we have a pipe. We have a pipe such that there is some bending in the pipe. Okay. So the bend is such that this bend in the pipe is actually equal to theta here from the horizontal. So this cross-sectional area is the same in both the locations. So this is B and this is also B. Okay. And the bending has an angle of theta, and what we have been asked to find, and let's write the case, we have been asked to find F star A for invested flow and B for turbulent flow. Okay, so this is what we are asked to find, and we have been given the velocity of inlet as u. So how will we go about such a problem like this? So we have been asked to find F star for invested flow and for turbulent flow. Now, the way we should think about this problem is that we have three equations for macroscopic balance: mass balance, momentum balance, and energy balance. And we have to use all three to actually arrive at the answer. So how? So first let's draw the control volume. Naturally the control volume will be the entire pipe. Control volume will be the entire pipe, just to show this. And let's, to simplify, although this is a system in cylindrical coordinates, so let's just write this in x and y just to make life easier. I will write x as z and y as r. This is just to make it a little bit easier, because let's call this as this is y. You can do an r and z also, which is totally fine. So the reason I'm doing it, because we'll have to find n1 and n2 vectors. Alright, so we have this control volume, and first thing we can very quickly see is do the mass balance. So mass balance tells us that V1 S1 is equal to V2 S2, right? And V1 is U, because this has been given to us that the velocity is U. US2, and we can basically say that velocity 2, sorry, velocity 2 times S2. In other words, that velocity 2 is also, that is quite straightforward, but still just to clearly write this through formal derivation, that if the diameter is d, S1 is equal to S2 for both inlet and outlet, and we have this. The second thing we need to do is we need to understand that for calculating F star we need the pressure drops, and we have rho v square and we can neglect the effect of gravity. Let me also clarify that neglect gravity. So if we can neglect gravity and we have to find this F star, then we know the velocities are same, and all we need to do is to find the pressures. Okay, so let's do the second part, which is F star is, and n1 is minus of ex. That's why I wanted to do this in x and y to make it a little bit easier. But n2 here, n2 vector, so think of it like this, that the tangent to this pipe, this part is this part here, the normal to the surface is actually basically this part, and this makes an angle theta with the horizontal. So I can write, and this will go outwards from the control volume. This will go outwards from the control volume. So n2 vector is actually equal to cos theta ex minus sin theta ey. Okay. So n2 vector is cos theta ex minus sin theta ey. Write it more clearly. Cos theta ex minus sin theta ey. Okay. So for F star, we can write this as minus of v1 plus rho u square. It is turbulent flow, so I can directly use mean velocity square of mean of velocity square is equal to mean velocity square into n1, which is minus of ex times s, which is the area, which is same in both s1 and s2, minus of p2 plus rho u square, because again velocity 2 is equal to u, and velocity square, mean of velocity 2 square is also equal to mean velocity 2 whole square, which is rho u square, into n2, which is cos theta ex minus sin theta ey into s. Okay, and let's write this down as p1 minus p, properly, p1 minus p2 cos theta into rho u square into 1 minus cos theta into ex plus p2 into sin theta into rho u square theta. Okay. So this is something that we can easily follow just by using the using of n1 and n2, and this is very similar to what we have done in recitations in the Monday which just went by. This is very similar to what we did there. Now the thing is, we have been asked to do this for inviscid flows and for turbulent flows, right? And the difference in those cases is that for a given velocity, the pressure drop that we are basically finding, P1 minus P2, would basically be different, and that is the whole point of this exercise. That the way we will calculate that is what basically uh, is important for our system. So let's let us go into the third thing, which is uh, the energy balance or the mechanical energy balance. And for inviscid flow and turbulent flow, the mechanical energy balance will be different, and that will basically change this P1 minus P2 and P2 here. Mainly, basically, we can assume P2 to be 0, and that will change P1 minus P2. So let's just first write these balances. So for inviscid flows, For inviscid flows, P1 we can, for inviscid flow again we can write this v cube by 2b as v square by 2 because it's a turbulent flow. And for inviscid flows, so in this pipe system we are not doing any work. There is no pump. We're not rotating any turbine, so we're not losing out energy or we're not putting any energy. Rho is constant, so we don't have any losses because of compression. And in inviscid flow, in inviscid there is no viscosity. There is no viscosity, so the viscous losses are basically also equal to 0. Okay, so we can write that delta of v square by 2 plus p by rho plus th is equal to 0. Because there is no change in height, we can also remove this. In other words, p1 by rho, p2 by rho plus v2 square by 2 minus p1 by rho. So delta means p2, we first evaluate this as 0.2 and then evaluated at 0.1. This is what we get, where 1 and 2 are again at this point and this point. So if you do that, because we know velocities are same from mass balance, basically what we are saying is there will be no pressure drop. Okay. So if that happens, our F star is P2 sine theta plus rho u square sine theta dy. Now this is extremely important. So first this part goes away while calculating because P1 is equal to P2. This part goes away. Sorry, and there is also a term from Px. Just write that down. The first part goes away, but there is still some part due to pressure and some part due to the plus rho u square into 1 minus cos theta into Ex. Now this is extremely important because so what I'm doing is I'm saying for inviscid flows from mechanical energy balance there is no work done, there is no viscous loss. So P2 minus P1 is basically 0, or pressures are same, there is no pressure drop. And that makes sense that there should not be any pressure drop because do not need any energy to pump the liquid if the fluid is purely inviscid. There will be no viscous loss. However, that does not mean that the force will be 0. There can be some forces on the wall, and that is the point, that even if you have inviscid flow, there can still be some force which you are applying to the system, F star not necessarily 0, because the fluid is going through some bending. So now if I put theta is equal to 0, if we put theta is equal to 0 degrees, and you will find that F star is equal to 0. If put a theta equal to 0, cos theta becomes 1, so E goes away, and sin theta becomes 0. And theta is equal to 0 means a flat pipe. The pipe is flat. And because of that, you can imagine that if you have theta equal to 0, then the pipe is flat. So there is symmetry in the flow. There is no asymmetry in the flow. There is no bending in the flow. So in case of inviscid flows, F star can be non-zero whenever there is bending in the flow or whenever there is asymmetry in the flow. But if the flow is symmetric, that is, if I reverse the flow and it is exactly there is no difference if I am having the flow from coming from here to going from here to here or going from back, it's the same because there is symmetry in the system. Then you will have star to be 0. But if there is any bending, any sort of asymmetry, then the system will not have a 0 F star. So it is a misconception among a lot of students that F star is only because of, so we define F star as the force on the walls by the fluid, and a lot of students think that the force is only on the walls is only due to the viscous stresses. It is true that in generally walls will experience viscous stresses, but for inviscid flows also there can be force on the walls. And this is something you can recall in the problem that T is solved in office hours when we did a problem over a flow over a half cylinder. When there was asymmetry in the pressure and there was a lift force. So the force need not be zero. So the whole point of doing this video is to clarify that F star is the force on the walls, but it can be non-zero for inviscid flows. Okay, it can be non-zero for inviscid flows. So there was no pressure drop, there was no loss in the pressure, but still you can have the force to be non-zero when there is some bending in the system. If the profile was flat, if theta was zero, F star was zero. So the flow was exactly going in a flat direction, so you did not have any force. So I hope that this makes sense. This is for inviscid flows, but what happens for turbulent flows? So for turbulent flows, our F star would actually be generally this part of P1 minus P2. So our F star would be of this part, this exactly part, but for P2 minus P1 we cannot neglect the viscous losses now. So I'll write it down here. For turbulent flows we can write that P2 by rho plus V2 square by 2 minus V1 by rho minus V1 square by 2 is actually equal to minus EV, which is the viscous loss per unit mass, right? And if you do that, you can get EV by rho, EV by W is actually equal to P1 minus P2 by rho. Okay, and depending on the viscous loss, which will depend on the Reynolds number of the system and or the friction factor, you can calculate this P1 minus P2. And don't forget, for different theta there will be different energy losses due to bending of system. So for theta equal to 90, which is basically a 90-degree bend in your pipe, your book, if you look in the book, you can have losses due to bending, and there is a table which actually explains the losses due to how much losses you will have due to bending, which is table 12.1. So you will have to account everything in the viscous loss term, the losses due to bending and the losses due to just flow in a pipe. So once you do that, you can then calculate P1 minus P2. Now, if P1 minus P2 is large, uh, so first thing is that P1 minus P2, that P1 minus P2 is not equal to 0. That is clear for turbulent flows. What is the value will depend on theta and Reynolds number, right? So if P1 minus P2, if we have a large theta, that is, let's say 90-degree bend, in that case, you can imagine that P1 minus P2 will have a P1 will be large. That there will be some losses uh, uh, because of bending also that we have to take into account. So because of all that, basically you will have you will see that you will have a very different profile for F star just because P1 minus P2 is no longer equal to 0. Even if we put theta equal to 0, which is a case of flat or straight pipe, if you put theta equal to 0, you will have this term of P1 minus P2 here, and thus you will not have everything to be taken as so what I'm trying to say is that you will have some non-zero F star even for theta equal to 0. Here for theta equal to 0, your F star was actually equal to 0, but in the case of uh, viscous losses, you will not have such a system. You will, in case of turbulent flows where you will have viscous losses, this P1 minus P2 cos theta will not be equal to 0 even for cos theta uh, theta equal to 0 or cos theta equal to 1. Okay, so let me summarize this a little bit. I hope what I was trying to say. So if F star is equal to 0, that means that the flow is inviscid as well as symmetric in pressure profile. It was only the case of theta equal to 0 in the example we discussed. If F star is not equal to 0, the flow can be both inviscid and turbulent or laminar. In this case, I will just write turbulent. Basically, you can have viscous losses, right? And within turbulent, and when within f star is not equal to 0, f star in case of turbulent flows will technically be larger than f star in case of inviscid flows, and that is expected because you will have a larger pressure drop due to loss in bends, loss in flow. So f star in turbulent will be greater than f star in inviscid. Okay. So I hope this video was useful in sort of trying to explain you that we can combine all the three balances that we have discussed, and that you are able to understand the meaning of F star. So F star is the force on the walls by the fluid. And we do that because you don't have to solve for the entire profile in the system, velocity profile, and you can get an idea of the entire force in the system just by using this equation of momentum balance. But to calculate momentum balance, you need pressures and information about pressures and velocity, and generally you can first use the mass balance equation to understand the relation between velocities. Then you can use this equation of energy balance to relate pressures depending on viscous loss and flow regime. And then you can put into momentum balance to calculate stuff. So I hope this video was useful. I'm sorry if I rushed a little bit at a few points. If you have any questions, feel free to write to us, and we'll hopefully uh, be able to resolve your recurring questions through videos, and feel free to give us any feedback in general. Thank you.